Hello, everyone. Welcome to today's session. We're going to be covering Gen Chem today with a bigger focus on like acids, bases, and electrochem, but we'll start from the top. Yeah, I think I'll just get started. People can roll in. As I've been doing for the past few days, we'll have like practice passages at the end. A few less questions today. I think there's a little more content in today's session. So at any point, again, feel free to put in the chat or unmute any questions you may have as I speak. So starting off with like the absolute basics. This isn't comprehensive, but we'll still start from square one in terms of just an atom is made up of subatomic particles, protons, neutrons, and electrons. Protons positively charged and neutrons are neutral. Those two are in the nucleus, whereas electrons are outside in orbitals or the electron cloud. The relative mass of protons and neutrons are about equal, and if you weigh them at 1, then an electron is almost a mass of 0. So electrons are pretty weightless. Protons and neutrons are really what make up the mass. The amount of protons in an atom is basically what makes it unique. That's like the atomic number is the number of protons, and so every element has a unique atomic number. Isotopes occur when you have the same element with the same number of protons, of course, but a different amount of neutrons. So for example, for hydrogen, the different isotopes are protium, deuterium, and tritium. So they have like 0, 1, and 2 neutrons respectively. And so all of them will have 1 proton, making it hydrogen, and the mass will be different. So the mass number is 1, 2, 3 for these. So you add up the protons and neutrons again. Also, just for point of clarification, when I say mass number and atomic mass, that's different from atomic weight. The difference there is that atomic mass and mass number are just by adding up the protons and neutrons, but for atomic weight, it's when you average between all the isotopes, and that's the one you'll see on the periodic table. You do get a periodic table on the MCAT, so you don't have to like memorize every element ever. And so for atomic weight, so an example I put here is for chlorine. So chlorine will have 2 naturally occurring isotopes. There's chlorine 35 and chlorine 37. So that 35 and 37 are the mass numbers there, but chlorine 35 is 3 times more abundant. So when I say weighted average, it's also like weighted by how prominent they are. And so since chlorine 35 is 3 times more abundant, the periodic table lists the atomic weight as 35.5. So that weighted average will favor 35 because it's more abundant. So that's kind of why we have those decimals on the periodic table. And that's also good to know, just the difference between those terms if they come up. Another way to describe atoms is through quantum numbers. It's good to know if you're given quantum numbers, how to relate that to an atom and vice versa. So there's 4 main quantum numbers. The principal quantum number describes the average energy of a shell. And so in the picture there, that would be like the 1, 2, 3, 4 as you go down. For the S block, for example, it's equivalent to the period on the periodic table, but you can see for like the D and F block, it's a little different. So like an element in period 4 is actually in like the 3D block, so it's important to note that. But for S and P, it'll actually correspond to the period. The next quantum number L describes the subshells within, so that's S, P, D, F. So 1 for S, 2 for P, 3 for D, and 4 for F, and that's like where in the periodic table it is. And then the magnetic quantum number, which is like M with a subscript L, specifies the particular orbital within a subshell. So these numbers are going to get you down to an exact electron. So the ML will tell you where in the subshell that electron is, and then the spin number. So every shell will have like an up and down spin. So you have a plus or minus half to tell you if it's like the positive or the negative electron. So good to know those and just know the quantum model. There's also just like the theory leading up to it, but getting into that would take a lot of time. So just good to know all of quantum. Another way to represent the periodic table is by the groups. So there's like alkali metals and alkaline earth metals, transition metals in that D block. And then at the end, there's the noble gases that aren't reactive. Next to them, the halogens that are very reactive. So it's good to know the different groups and some of their properties. I have like kind of a summary here. So for alkali metals, they easily lose an electron to become like noble gases. them and then the alkaline earth metals, those are the most reactive of all metals. The oxidation state of alkaline metals is +1. For alkaline earth metals, it's +2. Then I guess another one that's important to know is halogens. Those will react mainly with alkali metals. They take on an oxidation state of -1, so they like to gain an electron to become like a noble gas. And those have like the highest electronegativity, so those are some of the most reactive. Noble gases have a fully filled valence shell, so those are the least reactive. Helium, neon, argon, for example, and their electronegativities are like virtually non-existent. So they don't really have any electron affinity. They don't want to give or take electrons. The transition metals in the middle, what's interesting about them is they can take on multiple oxidation states. So they can form complexes with nonmetals, and you might know that like you can have different ways. For example, like iron and oxygen can combine in different combinations because they can take on different oxidation states. So those are probably the most notable groups. Another concept that's important is effective nuclear charge. A lot of factors kind of determine it, but it's kind of like looking at core and valence electrons separately. So if you have like aluminum in the photo on the right, you can see if you split up into its shells with the octet rule that we'll get into, you have like the outermost shell, and those are the valence electrons. But valence electrons will experience kind of less charge depending on how many core electrons shield them, so kind of how far away they are from the nucleus. And so you want to know how many valence electrons you have, how many core electrons you have, and then that kind of determines your effective charge. You have the equations there. So the shielding constant, kind of like your number of core electrons approximately. So you take the nuclear charge and subtract the number of shielding electrons. So if you have like 13 protons and then 10 shielding electrons, so like 10 core electrons that aren't in the valence shell, then your effective nuclear charge is 3. So that is like an approximation, but that kind of helps show like the effective nuclear charge and other factors that determine it. So on the left there, of course, your positively charged nucleus, and that's why I use the number of protons, the electrons in between, and then the electrons of interest will be usually valence electrons. So when they say electrons outside, usually no effect because you're usually talking about valence electrons that are the outermost. Trends on the periodic table, these can all be related back to effective nuclear charge, but it's good to know all these trends and how they are changed as you go across, as well as up and down. So as you're going kind of to the top right, you can say so to the right and up, you have increasing electronegativity, increasing ionization energy, decreasing atomic radius, and increasing electron affinity. I guess I won't get into the why, but it's important to kind of understand why that is. As you go down, you're getting more shells. As you go across, you're getting more protons in the same amount of shells. That kind of explains most of it. But for atomic radius, for example, as you go down, it's increasing because of the shells. As you go across, even in the same number of shells, you have more protons. So there's like a stronger positive charge that's drawing those shells closer. So it's good to know these trends, but also if you understand what's backing the trends, you don't necessarily have to memorize this. You can kind of deduce it yourself. So that's kind of the goal with a lot of the things here. The octet rule that I mentioned earlier, the way atoms tend to bond with other atoms are so that they have 8 electrons in the outermost shell, and so they form a stable electron configuration like the noble gases. So argon, a noble gas there. The innermost one will have 2, and then after that it's like 8 and 8. There are some exceptions though for incomplete octets. Some elements are stable with fewer than 8 electrons in their valence, so hydrogen and helium will have 2. So like the innermost shell usually just give 2 electrons. Lithium with 2, beryllium 4, and boron 6. Some elements can have expanded octets, but they'd have to be in period 3 or greater, so third row of the periodic table or further. They can actually have more than 8 electrons in a shell, so like phosphorus, sulfur, chlorine, for example. And then any molecule with an odd number of valence electrons, they can't distribute those to give 8 to each atom. So like nitric oxide, for example, has 11 valence electrons. For bonding, oh, those are supposed to be the same slide. So VSEPR theory, is another theory about electron density and what the shape of a compound will look like. So if you look at like the example compounds, the shape and the angle between electron pairs can vary. So for example, if you have like CH4, that's a tetrahedral shape. So you have the central atom, carbon, and then the 4 hydrogens branching off. VSEPR is valence electron shell pair repulsion theory. So it's good to know why things will be in different shapes. The same kind of formula can still have different shapes. So like it could be, is it like 3D? Is it planar? Good to know those things and how you can determine the shape of a compound. So that's important. From here, chemistry kind of turns into more equation or math-based things. That was kind of like the quantitative side or qualitative side, and now moving to the quantitative. The basics is moles. Using Avogadro's number, that is like 1 mole of something. So if you wanted to see the moles of something for its mass, you would divide that mass of the sample by its molar mass. Again, molar mass would be the mass of 1 mole of something. And the gram equivalent weight would also be the molar mass divided by the amount of moles. And so you can kind of figure out the amount of equivalence of something from that as well. Another thing that's important to know is like percent composition and percent yield. So percent composition is if you have the mass of something in its formula divided by the molar mass, and then percent yield, a lot of like the experimental passages could come up with something like percent yield, and so that's like the actual yield divided by the theoretical yield. So how much you actually got divided by how much you were supposed to get times 100%. Next concept is kind of kinetics, which we covered a little bit during biochem, but kind of going back to the reaction diagrams and a reaction coordinate. The first one there is just showing if you're going from hydrogen and chlorine to forming hydrogen chloride, your free energy will like increase and then eventually decrease. So you have that activation energy if you're doing the forward reaction, which is like just that bump you have to cross. The reverse activation energy is if you're going from like the products to the reactants, in this case, higher barrier. And then the delta G is just looking at the overall free energy change from reactants to products. So activation energy is looking more at the path. Delta G is just looking at the start and end. If you have an enzyme, it usually lowers the activation energy. So you catalyze the reaction, that would be like the green line on the right there, and you lower that barrier. But enzymes can't actually change the free energy of the reactants and products. So that start and end point will be the same. It's just a lower bump to have to cross. If you have a reaction that's like your coefficients are lower cases, let's say, and then your reactants are A and B, and your products are C and D, the rates will be equal, and if you adjust by the coefficient and the reactants being a negative rate and the products being a positive rate. So for example, the change in the concentration of A over time, negative, and also divided by the coefficient of A. So if you have like 2 of that, for example, you divide by 2, will be equivalent to the change in B, and then the positive change in C, positive change in D over time. So just that you have to account for the coefficients. And then the rate law will be your rate constant, the lowercase k, and then you only take the reactants and their concentrations. The x and y will be like the coefficients and what order they are, but that's not necessarily the same as the coefficient in the balanced equation. That's something that you'd have to find out experimentally, or it'll be given to you. So if a rate law is, say, like 0th order with respect to A and 2nd order with respect to B, for example, it would be like concentration of A to the 0, so it basically doesn't matter, and then concentration of B squared. So that would be like experimentally. Another thing you might get is you might get like a table, as you probably have seen, and then you actually see the rates depending on how much of A and B you start with. And so you'd have to figure it out yourself that like if you double B, the rate gets like quadrupled, then you'll know it's squared. Arrhenius equation is an equation for finding that rate constant K. And so it's proportional to the activation energy, well, like exponential of the activation energy, as well as the gas constant and temperature. So those are all factors that affect the rate constant and just how fast a reaction proceeds. Temperature is important, activation energy. And then for radioactive decay, the concentration of something at a certain time would be the initial concentration times the exponential of the negative rate constant times time. So that's another equation that's good to know if you get a radioactive decay question. More about radioactive decay will come up in like the physics reviews in terms of like alpha and beta particles and such. Another concept with like kinetics versus thermodynamics, you can control a reaction based on kinetics or thermodynamics, or you might say like there's a different set of products, the kinetic product or the thermodynamic product. And what that all really means is, again, thermodynamics looks at your start and end and just that overall delta G, whereas kinetics actually looks at the path you have to take and the activation energies to get there. So if you have your starting in the middle there, the thermodynamic product would be, if you go on the right side, the one that has the greater negative free energy change. So if you're trying to figure out which of these products is a thermodynamic product, you would just look at the product lines, which one's lower, that's the thermodynamic product. To find the kinetic product, you would actually look at the top of the graph and you'd see what's the lower barrier that we have to cross. And that's the one on the left there, where that transition state is lower energy. So it's easier to get through that path. That's a lower barrier that you have to cross. So your intermediate is also kind of in between there. So that delta G double dagger, kind of like the line with the two lines across, that's the transition state energy change. So you look for a lower one of those if you're doing the kinetic product, or you have kinetic control over a reaction. And then thermodynamics would be the greater or the lower free energy of the product. For equilibrium, so if we have the same type of reaction going on, for an equilibrium constant, you would need the concentration of products and reactants. So that also changes, I guess, from like the rate law. The rate law, you only look at the reactants. For equilibrium constant, it would be the concentration of the products to the exponent will be their coefficients, and then the denominator is the reactants, and again, the exponent is their coefficients. If you have the concentrations and you already know what's at equilibrium, then solving that equation will give you KEQ, like the equilibrium constant. But if you just have the concentration, you're not sure if you're at equilibrium, then you're getting Q when you solve this. You're getting the reaction quotient. And so then if you know KEQ and you solve for Q, you can see if the reaction is in equilibrium or not. So when Q is at KEQ, so when those concentrations solve this equation in a way you get KEQ, then you're at equilibrium. But if you solve for Q and it's less than that, then the reaction will be proceeding forward. If it's greater than KEQ, the reaction will proceed in reverse. So whatever has to be adjusted to get to KEQ. For thermodynamics, bunch of equations, but I guess I'll break them down. So the first one, the first law of thermodynamics is just the change in internal energy. You have like heat energy and work, so Q and W, where Q, when you don't have a phase change, is MC delta T, kind of looks like MCAT. So mass, then you have the, excuse me. So for when you don't have a phase change, you're just changing temperature. It'll be the mass, and then C is just your constant, and then the change in temperature. But if you have a phase change at that point, you multiply the mass by either, say, like the heat of vaporization or freezing, whatever the phase change you're having is. And then, oh, sorry, C there, the constant is heat capacity. And then if you're trying to find the enthalpy of a reaction, that delta H will be the enthalpy of the products minus reactants. And then at standard state, you can just take the standard state of forming the products minus forming the reactants. So you would be given those values for formation usually. Another way to think of enthalpy as like in terms of bonds, the enthalpy of reaction would be the bonds broken minus the bonds formed. So you look at those enthalpies. In any case, whether you're looking at formation or bonds breaking and forming, you'd be usually given those values. You don't have to like memorize them for anything. Only thing that's good to know is like heat of formation for is like a naturally occurring element is 0. but the rest you'd be given. Entropy is like the reversible heat energy divided by temperature. And then the second law of thermodynamics is that entropy is always increasing. So entropy of the universe, which is the entropy of the system and surroundings added together, is greater than 0. Standard entropy of reaction is the same thing kind of as the enthalpy. It'd be products minus reactants. And then Gibbs free energy combines enthalpy and entropy, so it's delta H minus Ts. That's a very important equation to know. And then again, for like standard state, you could also just take like formation of products minus reactants. Another equation for delta G of reaction in standard state is negative RT ln KEQ. So if you have the equilibrium constant, you can also use the ideal gas constant and temperature to get to G. So it's good to know when there's multiple reactions that can get you to the same thing. Sometimes you might be given like RT and K and you have to get to like S or something. It's good to know that like the linking step there is to solve for G, because both of those, they're in different equations. You might not find an equation where they're together, but you can solve for G and get from one to the other. And then if you have the reaction quotient instead of the equilibrium constant, then like if you're not at standard state, you can if you have like the standard state Gibbs free energy, you can add RT ln Q. Or you could do RT ln Q over KQ depending on what you have. So that's like the different thermodynamic equations. Moving on to gas laws, so even more equations. These are just kind of like the mathier concepts of Gen Chem. We have ideal gas law, of course, PV equals nRT. Density of a gas is mass over volume, which if you're kind of getting that from ideal gas law, you can also arrange that as like PM over RT. So that's pressure and molar mass divided by the gas constant and temperature. So then there's a bunch of different gas laws that are kind of combined into PV over T is equal to PV over T. So if you have pressure, volume, and temperature of a gas at one point and another, that quotient will be equal. But if you look at those, if you kind of break that down into the two variable pairs, you have P1V1 equals P2V2, that's Boyle's law. So it's just that like that product PV will stay constant. There's also Charles' law where V over T stays constant, and Gay-Lussac's law where P over T stays constant. So any part of that PV over T, you can like only use two of those and those will still be constant. There's Avogadro's principle as well, where the number of moles divided by volume is also a constant. There's Dalton's law, and so that's like partial pressures. If you have partial pressures of like the different things, if you have like oxygen, carbon, and hydrogen, you can add up those pressures to just get the total pressure, which is really neat. So then also because of that, you can figure out partial pressure from total pressure by knowing the fraction of that gas. Henry's law, if you have Henry's constant, that's like the KH there, then you can solve for like pressure, concentration, one with the other, and that Henry's constant is basically just the ratio of concentration divided by pressure. Kinetic energy of a gas, similar to the physics formula, half mv squared. You can also put that as 3/2 kb, so the Boltzmann constant times temperature. The root mean square speed is the square root of 3 times the gas constant times temperature divided by molar mass. And then Graham's law, also kind of related. The ratio of rates, you'd have to square root the ratio of molar masses, but inverse. So it's like 1/2 on the left, 2/1 on the right. So those are for like effusion. And then when ideal gas law doesn't necessarily work, I mean, it's an ideal. Another model is the van der Waals equation of state, and it introduced two constants, A and B. So it kind of adjusts for like how real gases will take up some volume themselves. So that's why you're kind of subtracting something from the volume. And so that equation is written there. I guess I won't read it all out, but if you had to use that, they would probably give you the equation and they'd give you A and B because those are constants. But it's also just good to know that there are different equations of state, or they could throw a different one at you. There's a ton, but there are different like constants you can introduce to make ideal gas law closer fitting to a real gas. So something to look out for. For solutions, percent composition, if you're going by mass, it would be the mass of the solute divided by the mass of the solution as a percent. Mole fraction of, say, something like a molecule A, moles of that divided by the total moles. Molarity is moles of solute divided by liters of solution. So that's like what you're dissolving divided by liters of the whole thing. Molality is moles of solute divided by kilograms of solvent. So that's kind of important to know the difference between, I guess molality isn't used as often, but you're taking the weight instead of the volume of the solvent that you're using. Dilution formula, basically what that stems from is that you're keeping the same amount of moles. So you have your molar mass times volume, initial and final will be the same. And then your solubility product is kind of like the equilibrium constant, but KSP instead. You have like your concentrations to the exponent of their coefficients, but instead of having kind of reactants and products, you're kind of thinking of it as if something were to dissolve. So you have like a solid that splits up into ions. In that case, you would only be looking at those aqueous ions in your equilibrium constant. And so that's why you don't have the typical denominator of like the reactants, because your reactant is that solid that you just kind of take out of it. And so you would just have the ions that it splits up to. And then you're kind of, this formula kind of extrapolates what the constants would be, because it would just be like crossing the charges over. But if that's too fancy, you can just kind of look at the balanced reaction. Ion product, similar concept. Raoult's law is for vapor pressure. And so the gas fraction times that vapor pressure can get you the pressure of that gas. There's also some of these other boiling point elevation, freezing point depression, and those are also less common, or in the osmotic pressure, those are less common, but it's good to know. I in all of those is the Van 't Hoff factor. And then you have your constants for like boiling or freezing, KB, KF, and then the mass. So those might be equations you run into that would just show like the change in temperature at the boiling point or freezing point. Then we get into, I guess, the heavier topics of Gen Chem, acid bases and electrochem. So for acids and bases, there's a lot of different theories. I guess the three that I would say are most important are Arrhenius, Bronsted-Lowry, and Lewis. So it's good to know the difference between those, because not everything qualifies as an acid and base if you're talking about a different theory. So for Arrhenius acids, those are the ones that dissociate to just produce hydrogen ions, and then bases dissociate to produce hydroxide, OH negative ions. So that's like the H plus and the OH minus are what make acids and bases. For Bronsted-Lowry, the acids are species that can donate hydrogen ions, but then the bases are species that can accept hydrogen ions. So it's not about producing hydroxide ions, is kind of the difference there. And then Lewis is actually more focused on the electrons rather than ions. So it's just the acids are electron pair acceptors and the bases are electron pair donors. When relating between the different theories, all Arrhenius acids and bases are Bronsted-Lowry acids and bases, and all Bronsted-Lowry acids and bases are Lewis acids and bases. So it kind of gets wider, but then the reverse is not necessarily true. So like Lewis acids and bases are not always Bronsted-Lowry, and Bronsted-Lowry aren't always Arrhenius. So you could think of like Lewis as kind of like the broadest category. Bronsted-Lowry and Arrhenius are more specific, because something can be like an electron pair donor, for example, but it's not necessarily producing hydroxide ions. And then there's amphoteric and amphiprotic species. So amphoteric means it can behave as an acid or base. Amphiprotic is like a specific type that can behave as a Bronsted-Lowry acid or base. So for example, water, because that can donate or accept hydrogen ions. These are the equations that come up when dealing with acids and bases. Kw, or the ionization constant for water, that's if you multiply the concentration of hydronium ions and hydroxide ions, that's 10 to the negative 14 at standard temperature. And then you define pH and pOH, so power of hydrogen and power of hydroxide. So for pH, it's negative log concentration of H plus, pOH, negative log concentration of OH minus. When you're thinking like a negative log, that's also the same as kind of like logging the reciprocal, but either way. The relationship of pH and pOH, based on that first equation, those add to 14. So on the scale in general, they'll be going from 0 to 14, and if you have one, you can subtract from 14 to get the other. That p-scale value approximation is kind of a math trick where if you have something in like scientific notation as n times 10 to the negative m, you can approximate the p-values, whether it's like pKa or whatever, as m minus 0.n, so that original number. So you just have to like slide the decimal one position to the left, I guess you divide it by 10, and then subtract that from that exponent. So like for example, if you have a Ka of something that's like 1.8 times 10 to the negative 5, and you need the pKa, again, you don't have calculator on the MCAT, the approximation here would be that if you have 10 to the negative 5, that's like your m, so you have the 5 there, and you subtract, so I guess you rearrange the log, and it would be like 5 minus log of 1.8, so you can shift the 1.8 over to be like 0.18, and so it'd be like 5 minus 0.18, you get 4.82, which is pretty close to the actual thing. I think the actual one would be more like, it'd be about 0.1 less, but that's just like an approximation when you don't have a calculator, an interesting rule. And so then, yeah, speaking of Ka, the acid dissociation constant, and the base dissociation constant, Kb, you can kind of just get those from writing out the reaction of the dissociation. Like if HA goes to A minus and H3O plus, this is like what the K, the equilibrium constant, would be. The relationship of those is that Ka times Kb, so if an acid and its conjugate base, or a base and its conjugate acid, will equal Kw, so that 10 to the negative 14. For titration, the equivalence point will be just kind of when you have equal amounts of your acid and base that you're titrating. So that's the reaction for that there. Henderson-Hasselbalch is if you're using buffers, then your pH is like your pKa plus the log of your A minus divided by HA in concentration. So the ion divided by the acid, and then similar for pOH in a base. So those are the equations that are good to know for acids and bases. Then the next thing is oxidation and reduction. For electrochem in general, there's a lot of good mnemonics that kind of help you remember the rules. So for defining oxidation and reduction, I think the one I use a lot is Eulerig, where oxidation is the loss of electrons and reduction is the gain of electrons. There's also like Leo the Lion says Gur. Another one that I didn't know of, but the Kaplan book has, is Leora says Guroa, but that one also, I guess the benefit of that one is that it shows that like reducing agent and oxidizing agent are kind of confusing terms, but if it's undergoing oxidation, it's the reducing agent, and then if it's undergoing reduction, it's the oxidizing agent. So if you have something that's losing electrons, it is the reducing agent, but it's undergoing oxidation. So that is good to know. The table at the top there has just some common oxidizing and reducing agents. And then in terms of like balancing equations and stuff for electrochem, you need to know how to assign oxidation numbers. So there's a good set of like rules on how to do it. For free elements, it's 0. No oxidation number is 0. For an ion, it's just the charge of the ion. So if you have Na+, the oxidation number is just +1. For group 1, those are +1. Group 2, those are +2. So like the alkali and alkaline earth metals. For the halogens, it's -1, except if there's something of higher electronegativity. So HCl, Cl is -1, but HOCl, O is the higher electronegativity, so that will dominate, and then Cl is just kind of like whatever has to be adjusting, so it's actually +1. And then for hydrogen, it's usually +1. It can also be -1 if it's with something that is less electronegative. So the alkali and alkaline earth metals, those will take number one, -1. So hydrogen would be +1 in that case, like in NaH. Oxygen is usually -2, but if you're dealing with a peroxide, that's -1, or something more electronegative than oxygen, so like fluorine, oxygen could be +2 in that example. And then also very important, the sum of the oxidation numbers in a neutral compound is 0. So if you follow the rules, there might be some things you just extrapolate to know that like something neutral has to be 0, and then if something has a charge, the overall oxidation number has to be the charge. So for SO4 2-, the sum of all those oxidation numbers, so S and then 4 times O, has to be -2. So that's like all the different rules for oxidation numbers. From there, you need to know how to balance reactions. So if you have the reaction at the top there, MnO4- plus I- goes to I2 plus Mn2+. So usually for these reactions, you're like given if it's in an acidic or basic condition, that comes into play when you're balancing. The first thing, the method is half reaction, so you want to split it into 2 half reactions, balance your atoms, balance your charges, and then add back together. So the first thing we do is split this into the 2 half reactions. So you have like the iodine and then the magnesium oxide. So I- is going to I2, and then MnO4- is going to Mn2+. And then for balancing atoms, if it's acidic, you want to balance everything that's not hydrogen and oxygen. Then you can add H2O to balance the oxygen atoms and H+ to balance the H atoms. And then if it's basic, use OH- and H2O to balance instead. So acidic, you would have an excess of hydrogen ions, whereas in basic, you'd have hydroxide ions. So that's kind of the difference. So if you follow steps down, so then the next step of balancing would be the one under there. So the bottom left, you need to balance the iodine. So you'd have 2I on the left. Your magnesiums are already, your manganeses are already balanced. So then you'd introduce your H+ if this was acidic, for example, and H2Os to balance all the atoms. Then you balance the charges. So for example, 2I- going to I2, you have -2 on the left side, but neutral on the right, so you'd add 2 electrons there. And then once that's all balanced, you can cancel out things that are on the left and right, and then add the equations together. So the bottom there is like the overall balanced reaction. So it's good to just like practice balancing some of these reactions, splitting them up and making sure you know the difference when it's an acidic or basic solution. And then more on electrochemistry, the cells are where these oxidation reactions take place, oxidation reduction. Electrodes are like strips of metals that are placed in electrolyte solution. And then you have the anode and the cathode, and then the mnemonic for that I use is like an ox and a red cat. So the anode is the site of oxidation, and then reduction is at the cathode. Electrons will flow from the anode to cathode, but current flows from the cathode to the anode. And then there are cell diagrams, which I believe I have one on the next slide, which kind of shows in shorthand what reaction is taking place. So for the electromotive force, that's the voltage or electrical potential difference in the cell. If it's positive, you have delta G -0, so it's spontaneous and it can release energy, and if it's negative, then it's non-spontaneous. So this cell in particular is called a Daniell cell. It's an example of a galvanic cell. So galvanic cells are the ones that house spontaneous reactions. So you have a delta G that's less than 0 and a positive electromotive force. So here you have like the zinc electrode in aqueous ZnO4, ZnSO4, and then a copper electrode in CuSO4. So the anode is the zinc bar, and you have like solid zinc oxidized to Zn2 plus aqueous ions, and then the cathode is the copper bar, and then you're reducing Cu2 plus, so copper ions into solid copper. You have the half cell reactions, which come down to the net reactions. So the half cell reactions would be like Zn solid going to Zn2 plus and 2 electrons, and then Cu2 plus 2 electrons going to Cu. And then the net reaction, the 2 electrons on both sides cancel out, so you just have net reaction there. You also have the shorthand notation written there, the cell diagram. And so basically reactants and products are listed from left to right, and then it's like anode, line, anode solution, and you want to put the concentration as well, and then the double line, then the cathode solution, and the line in the cathode. So a single line is a phase boundary, but the double line is like the salt bridge or another type of barrier. So that's like where the cell is physically separated. The salt bridge allows like cations and anions to exchange as well. So that's an example of a galvanic cell. The opposite is an electrolytic cell if it's a non-spontaneous reaction. And then those are battery powered or just powered by something, and then they can be used to create products because you're kind of like forcing something to plate. These are the reaction or the equations for electrochem. If you look at like the moles of electrons, it's going to relate to the charge on the element that you have in your cell. So for example, if it's like Zn2 plus 2 moles of electrons there. The electrodeposition equation, it's the moles of an element being deposited on a plate. So if you have like M is like the amount of metal ion being deposited, I is your current, T for time, N is the number of electron equivalents for that ion, and then F is a constant, the Faraday constant. So that's like for electrolysis. You can see how much of something's being deposited. The electromotive force of a cell, you need the reduction potentials of the cathode and the anode, and then subtract those. This change in free energy from a cell, standard delta G, you'd need the moles, Faraday's constant, and that electromotive force multiplied together. The Nernst equation is similar, where you have like, if you don't have it at standard state, then the electromotive force is the standard one minus RT over NF ln Q, reaction quotient. You can also kind of simplify if you're at standard temperature, that like RT divided by F. And then the change in free energy, negative RT ln K, we've seen that one, and then we've also seen that delta G is like standard state delta G plus RT ln Q. So those are kind of thermo coming back. Thermo and electrochem kind of tie in, as you can kind of see with like delta G and such. So how are we for time? Okay, about 15 minutes left. Feel free to drop any questions, and then we can also get into the passages. They're a little shorter today. This first one has 3 questions, the next one has 5. So I guess I'll give more time to the first one so you guys can read the passage. And yeah, again, drop any questions as we're doing this. It's a bit of a longer passage, but less questions. I'll give 30-second warnings when I'm about to flip the question. 30 more seconds for this question. Okay, this is question 2. Thirty seconds for this question. Okay, and then final question for this passage. Thirty seconds. Okay, so for these 2 questions, for the first question, it would be that LIF and AGI both precipitate. You'd kind of look at, I guess, similar things in the table. So for AG, Cu plus was considered soft, so AG plus in the same group would be considered soft. And then I minus is also soft, so AGI would bond together and then precipitate since they're both soft. And the passage said that like soft acids bind to soft bases, hard acids bind to hard bases. Similarly for Li plus, there's K plus in the hard acids, and so Li plus would also be considered a hard acid, and then that would bind with F minus, which is also hard, and so then both being hard ions, LiF would also precipitate. So that's why we get that they both precipitate. Then for the negative correlation, polarizability has, I guess, a positive correlation with softness, so it would be a negative correlation with hardness. for other things, like hardness has a positive correlation with charge density and electronegativity, I think, and then oxidation state as well, for looking at just like the an increase in oxidation state is an increase in charge density. And then for the last question here, it was that Hg plus and Br minus are soft ions. And so I guess a small KEQ is that indicates the reverse reaction is favorable, and a large KEQ will indicate the forward reaction is favorable. So we know that like the complex ion won't bind with F minus because it's a small KEQ, but it would prefer to bind with Br minus. And then for soft ions, we know that they'd like to bond with each other. We'd also see, I guess, Hg plus also being soft. It's in the same group as cadmium, and then that was a soft ion. So I guess it's just about kind of like relating the groups and figuring out the hard and soft. For this passage, I think the main thing that stood out was like, it's not a theory that we know or a theory that you're supposed to know, but just kind of extrapolating what you know about Gen Chem and like the property of different elements. And then when you're given new information or new theories, to kind of sort out the theory and the things you already know. So that kind of thinking skill. If there's any questions that remain or like my explanations weren't sufficient, feel free to ask in the chat. Otherwise, we're going into passage 2, I guess, just for time sake. It might go over with my explanation, but if you have to leave at 8, that's totally fine. So yeah, more time will be given to question 1. This is 5 questions. Luckily, a shorter passage though. "30 seconds. Okay, second question. "30 seconds. Okay, third question. Oh, 20 seconds on this one. Okay, question 4. Thirty seconds. And also, if you have to head out because it's 8, no worries. I'll post the slides in the files with the rest of them, and the answers are in the slides after this. Okay, final question. Thirty seconds. Okay, so getting into these questions, first one was just kind of like the anox red cat. It was given what's oxidized and reduced, so it's just about connecting that the anode is where oxidation happens and the cathode is where reduction happens. For this question, the 10 carbon saturated fatty acid, because of just the amount of electrons, more electrons will be more current. And so for this, what is most reduced is also like what can undergo the most oxidation, and that would just be the 10 carbon fatty acid. Those CH bonds have a lot of electrons, so it would just for the, I guess the 5 carbon fatty acid and the glucose are smaller. For the 50 amino acid long, it's, I guess it's just like there's less energy in those bonds. Those CH bonds can undergo the most oxidation. So that would be why it's the 10 carbon fatty acid. For harnessing the flow here, it's NADP plus. NAD plus is reduced to NADH during catabolic breakdown, like glycolysis and such. Electron transport chain also accepts the electrons. So those proteins and such, the dehydrogenase enzymes also facilitate like the oxidation of substrates. So it's NADP as well as like NADPH, which are mainly involved in anabolism and not catabolism. So those are used like in the pentose phosphate pathway and such. So I guess I was kind of tying to biochem. For this question, current, so again, flow of electrons, more current, more electrons. And so breaking down glucose in multiple steps will allow more electrons to be, I guess, oxidized from the glucose. So multiple enzymes would probably increase the current. And then for the last question, the wire, it's, I guess, an outlet for electrons to charge the light diode, but it's also a salt bridge, and so it can balance kind of like the positive charge in the anode and negative charge in the cathode by having ions migrate, and then otherwise your charge imbalance might get too great and the reaction would stop, but instead you can kind of replenish that through the salt migration, allowing the reaction to occur longer, as the option states. So that is all for the Gen Chem review. Thank you for staying extra time. If you have further questions, though, feel free to hang around. Otherwise, thank you for coming. For the last question, why wouldn't it also be D? Doesn't it drive electrons? Drive electrons to move from the anode to the cathode. I guess that's just one directional would probably be the reason. So the better answer, I would say, is replenishing the charges, because it's a two-way sort of salt bridge. You can have both directions. Does that make sense? Let me look at the passage again and how it explains the cell. Passage for electrons. I think the way in this for the wire for the electrons to move from the anode, I think in this case it is serving as the salt bridge. I guess that was kind of like the basis of my past response. So basically, the wire in this case it's serving as your salt bridge because it doesn't really drive the electrons to go anywhere. It's just like a path that they can take. So I guess the wire, the connotation is electrons moving, but it's not like you have a battery or anything. So you're not really forcing the electrons to move necessarily. It's just like the path. So in this setup, I guess the way they described it, it would be your salt bridge. But I guess that's not like how we typically think of a wire, which is why it's kind of different here. So it allows for the passage, but it's not forcing the passage. So it's not like you're gonna have like that forced one directional, like kind of like how you would in electrolysis. But it's just like it would be like the equivalent of when you have like a paper towel salt bridge. You just have that path for it to take. Does that make sense? Yeah. Okay. Great. Thank you.